And let us move to the next talk by Professor Victor Braguta.
Hello, everyone.
Yes.
I will try to share my screen.
Yes, yes. Are you sharing your screen?
No, just a minute.
Okay.
Can you see my screen? Can you see my screen?
Yes. Yes.
Okay.
But your desktop, not your slide.
I'm sorry, I don't know why I'm not able to show my slide. Just a minute, because now I'm looking to my slides. Just a minute. Let's try again.
Yes.
When you click to share the screen, you can choose what to share. I mean, slides or just.
But the point is that I see a table, but I don't see slides. At the same time, I see slides on my screen.
Yeah, but can you just share just your screen, the whole screen, and you like it would not depend what you see. So it's just your screen.
This can you see my slide right now?
Yeah, we can now.
Okay.
Okay, good. Please go ahead.
Well, I'm going to tell about our latest study of rotating gluodynamics, and this work was carried out in collaboration with these people, and partly our results has already been presented in this short paper, and probably in the nearest future we'll prepare. We are going to prepare the results of our slide in a longer paper, all our results. Okay, I'm going to start from the introduction, and I think that in this session, a lot of lecturers have already mentioned that if you have collision, heavy ion collisions, non-central heavy ion collision, in this case, quark-gluon plasma, it is reasonable to expect that quark-gluon plasma rotates, in addition to magnetic field, high temperature. And it is interesting to estimate the size of this rotation. What is angular velocity? It is possible to do this, for instance, from hydrodynamical simulation. For instance, there are a lot actually of papers devoted to such simulations. I would like to mention only one, because we need only to estimate the size of this rotation. This is collision of gold-gold. This is the parameters of this collision, and typical angular velocity is given in this range. And if we take, for instance, angular velocity 20 MeV, in this case at distance 7 Fermi, we have speed. The particles inside our fireball rotates with the speed of light. So we conclude this is indeed relativistic rotation of quark-gluon plasma. And also would like to mention the result of STAR experiment. In particular, they managed to calculate or to measure polarization of lambda bar particles, and it turns out that it is possible to relate these observables to angular velocity and thus estimate angular velocity, and the results are in agreement with hydrodynamical estimation. Probably it is better to say hydrodynamical estimations are in agreement. But anyway, we have similar angular velocity, I mean the value or the magnitude of this parameter, and again we have relativistic rotation. So it is for this reason, if this rotation is so rapid, it is interesting to study how rotation influence properties of QCD. And actually, this is my report is devoted to study this question. I would like to mention recent works. There are a lot actually of works In particular, mostly, I would say mostly of these studies are carried out within Nobuya-Lan-Lazini model, and they are focused on chiral transition. And they found that in these papers, it was found that critical temperature of the chiral transition drops with angular velocity. And what I would like to mention, very interesting, very reasonable, I would say, explanation of this, physical explanation of this fact. The point is that um, in rotating system, particles with spin or angular velocity polarizes and are polarized, and we know that chiral condensate is a scalar condensate, and for this reason, because of polarization, rotation destroys chiral condensate, and this lead to a decrease of the critical chiral critical temperature. In addition to these papers, which were carried out in Nobuya-Lan-Lazini, I would like also to mention the very recent paper of Mi Huang. She has given us she has told us about results obtained in this paper, and very important to note is that one of the prediction is that critical temperature of confinement deconfinement transition drops with angular velocity. Also, would like to mention paper of Professor Rat Imanota, where first study, latest study of rotating QCD was carried out. And in particular, we are going to we are going to follow this paper and conduct our study with this action, with discretization of this action, similar to this paper. Okay, now, so my aim is to study how rotation influence QCD properties. And in order to do this, there are few possible ways to do this. However, I'm going to follow the following idea. So we consider we switch to the rotating system where our system in thermodynamical equilibrium. And it is very important to notice that in this reference frame, we can consider QCD as in the external magnetic field, and thus carry out our simulation. So the problem of rotating is reduced to problem of QCD in external gravitational field. And also very important to note is that boundary conditions are extremely important, because if we go to very large distance from rotation axis, the velocity of rotation exceeds the speed of light. This is not cannot be realized in the real world. For this reason, we should control the distance from rotation axis to the boundary, and also specify boundary condition. This is very important, and I would like to notice that this problem is common for all approaches, not just lattice. Okay, now let's proceed to the details of the calculation. So in my report, I'm going to focus on gluodynamics, and as I already explained, we can see the gluodynamic in external gravitational field. The metric tensor of this field is very well known, and here you see the geometry of our system. So our rotation axis is in the center of our rotation volume, and we separate temporal direction and direction along this rotation axis from the transverse coordinates. This is transverse to the rotation, to the angular velocity. Next, let's consider how it is possible to carry out this study. As I already discussed, I have already told you that we consider system in thermodynamical equilibrium, and it turns out that since our metric doesn't depend on time, we can build a conserved quantity. This is Hamiltonian. I don't write it explicitly. It can be written. It is quite simple. For us, it is very important that this structure, this conserved quantity, and it is possible to build partition function with some parameter beta. I will explain you meaning of this parameter a little bit later. And using a usual technique, we can rewrite this expression in terms of path integral with the following gluon action. And here, this is metric tensor, but Euclidean metric tensor can be obtained from this one by analytical continuation from real time to imaginary time. And as a result, we get the full expression for the gluon action. Now, very important point is that we know from general relativity theory that there is a so-called Ehrenfest-Tolman effect, that in gravitational field the temperature is not constant in space and at thermal equilibrium. In particular, if we have temperature, which actually depends on distance to rotation axis, and in this case, temperature is not constant. Constant is temperature multiplied by square root of G00. And it turns out it is possible to show that this constant is not just an arbitrary constant, it's exactly 1 over beta, which are introduced in this partition function. Okay, if we put G00 from our expression, which I presented above, we can write the following expression and draw a conclusion that rotation effectively hits the system from rotation axis to the boundary. So effectively our system, if for instance we consider two systems, one rotates, one doesn't rotate, in this case the system that rotates is a little bit on the average it is has a larger temperature. And for this reason, from the very beginning, when we started our study, we thought that we could expect that rotation decreases critical temperature. And also very important to notice, because the point is that below I am going to use temperature, but temperature, it is very important to specify because temperature depends on distance, and temperature, this is temperature at on the axis of rotation, or in other words, we can say this is 1 over beta. Okay, now a few words about boundary conditions. You know that a lot of physics can depend on boundary conditions in this problem, and it's very important to specify boundary conditions. In order to understand how our results depend on boundary condition, we use 3 types of boundary condition. The first one is periodic, the second one Dirichlet boundary condition. So Dirichlet boundary condition when we put all linked variables on the border to unity, or this is equivalent to for potential gluon for potential equals to 0 on the border. And also Newman boundary conditions, so or open boundary conditions outside the studied volume. We have again plaquette variable equals to 1 or f mu equals to 0. I would like to mention that these boundary conditions affect differently to the physics in our system. In particular, for instance, we know that Dirichlet boundary condition violates Z3 symmetry. And for this reason, for instance, first order phase transition in gluodynamics turns into a crossover in our case. And also very important to note is that these 2 types of boundary condition violates they're not appropriate for the field of velocities of rotating body, at least on the boundary. But a Newman boundary condition doesn't violate some symmetry, and also very importantly, as far as I understand it, they much more appropriate for the field of velocities. And also very important to notice here, from the very beginning, we thought that these boundary conditions are very important. They can considerably modify our results. However, it turns out that they are not actually. I will, a little bit later, I will tell you how this works. About explanation of this fact is the following. The point is that system, if rotation is not very rapid, system effectively screen boundaries. And for this reason, the influence of the boundary conditions to our results are not very crucial, I would say. Okay, let's proceed to the sign problem. So let's consider our gluon action again, and we see here 2 terms which are imaginary. And this evidently this leads to sign problem. We're not able to use important sampling explicitly. Or so In order to avoid this problem, we use imaginary, so we go to imaginary angular velocity. As a result, the full action is real, and after we carry out our study, we conduct an analytical continuation to real values of angular velocities. And what is very important to notice here, this approach works up to sufficiently large omegas, up to omegas smaller than 50 MeV. So it means that implies that at least the results, I mean, estimation from star experiment are in the range where we can conduct analytical continuation. Okay. Now, I would like to discuss the observables that I'm going to study. First of all, critical. So we mostly focus on critical temperature, how critical temperature is affected by rotation. And we calculate Polyakov line. We average Polyakov line overall volume, very important to notice. And also we calculated, in order to calculate critical temperature, we calculated susceptibility of Polyakov line, and critical temperature is determined from Gaussian fit of the susceptibility. But before I proceed to our results, I would like to discuss an interesting question. You know that in QCD, there is non-zero condensate. I mean, not in QCD, in gluodynamics, there is non-zero condensate. And this condensate leads, or probably it originates from a violation of scale anomaly in gluodynamics. As a result, it can be shown that there is non-zero average of energy momentum tensor is not zero. It is given by this expression. This is energy density is proportional to this exactly condensate. This is in a system at rest, which doesn't rotate. But when we go to rotating system, we should expect that there is a non-zero value of flux of energy or momentum in some direction. I mean, and we calculated this. So in rotating frame, we calculate this energy momentum tensor, and indeed we found that it is not zero and it corresponds to rotation of condensate. So in our system, I mean, this is calculation at zero temperature. I would like to stress here this calculation of zero temperature. So at zero temperature, our ground state of our system is rotating vacuum. And to my mind, this is very interesting check, or that our results are in agreement with zero temperature no rotating system. And at non-zero temperature, we expect, and we found it, but I'm not able to show these results right now. We found that thermal component of our system indeed at rest in this rotating system. Very interesting, important point. Okay, now let's proceed to our results. This is a calculation of Polyakov line and also susceptibility, and for open boundary or Newman boundary conditions. And we see from this plot that if we have zero angular velocity, this is this curve. And if we rise the angular velocity, the whole curve goes to left. This means this implies that critical temperature decreases with imaginary. I would like to note that this is not angular velocity, it's imaginary with an imaginary angular velocity. The same is seen on the plot of susceptibilities. We see peaks and they move to the left. Again, decrease of the critical temperature. The same similar plots can be drawn for Dirichlet boundary conditions and also for periodic boundary conditions. And we also try to estimate how rotation influences the type of the transition. In particular, we studied how the height of the peak depends on the volume of our system. We found that for periodic and human boundary condition, it scales like a volume, but for Dirichlet boundary condition, it is constant. This is again, this implies that rotation that doesn't modify the order of the phase transition. Dirichlet boundary condition, I have already told you that it violates Z3 for this reason. From the very beginning, we expected that even at zero angular velocity or without rotation, it is constant. Okay, now let's proceed to the dependence of critical temperature on angular velocity. This is a critical temperature divided by critical temperature at zero angular velocity. It is angular velocity squared, and we see that all our data, first of all, that temperature decreases, and all our data are well described just one term. So it is sufficient to describe our data up to sufficiently large angular velocity only just one by one term. Then we conduct analytical continuation and see that critical temperature rises with angular velocity. Okay, now we have also checked, I'm not going to present these results in my report, but we have checked that our results weakly depend on lattice spacing, and they weakly depend on volume in Z direction. Okay, but what about transverse direction? What if we fix our angular velocity and vary our results in transverse direction? These two pictures show how this works. Suppose we fix some, each curve here corresponds to fixed transverse direction. So we see here 25, 29, and 23, 41 steps in transverse direction. And we see that the slope rises as we go to larger and larger lattice spacing, as a lattice size in transverse direction. So this means that this coefficient is not universal. It depends on the size of our system in transverse direction. But however, it turns out if we redraw this plot in terms not just angular velocity, but in terms of velocity of transverse velocity on the border of our system, it turns out that all lines lie on all points lie on one line, I would say. And it means that it implies that all our data for all transverse transverse sizes of our lattice can be well described by this very quite simple formula. This is velocity on the border. So this is implied that angular velocity is not actually a parameter which fully determines the system. Distribution of velocities, this parameter determines the system. Also, we studied how our result, these plots are very similar for all boundary conditions, but actually this coefficient also for fixed boundary condition, in some sense it is universal, but but it depends on the boundary condition. For instance, in periodic boundaries condition, this is approximately 1.3, for Dirichlet 0.5, and for Newman boundary condition 0.7. Okay, now I proceed to the conclusion. So we carried out latest study of how relativistic rotation influences confinement deconfinement transition. We found that critical temperature or confinement deconfinement transition rises with omega, but this is in contradiction with the result of which were presented by me Juan. And I would like to return to the result of Nobuyulan-Lazinian model, but definitely this is not latest result, but to my mind, very reasonable idea was very reasonable explanation of this result was given. In particular, from this explanation, we can expect that critical temperature of chiral transition drop with angular velocity. So it is interesting for the future. It is interesting to understand. So we have one temperature which goes up and another temperature which goes down, and it is very interesting to understand what is really happening in real QCD with dynamical quark, who wins, or probably these two transitions will be separated. I don't know, but it is interesting to see this. Okay, thank you.
Yes, thank you. Thank you for the very interesting talk. So we can pick some questions. The first one is from Nugza, please.
On the first slides, we have seen the temperature dependence, effective temperature dependence on the angular momentum. And we know that in hadron matter, we have Hagedorn temperature, maximum temperature, or in QCD language, phase transition, quark-gluon phase transition temperature, right? So we expect by that formula in rotation frame that at some velocity we reach that maximum temperature. Beyond of them, rising angular momentum, we have phase transition. Thus, simulation presented corresponds to these expectations. Question.
Well, I'm not sure that I understood your question correctly. You mean hydrodynamical simulations, right?
Right.
The point is that I'm not able to discuss these results because this is not my paper. So as far as I understood, they just apply some hydrodynamical approach, and there are a lot of peculiarities of this approach. And if you are uninterested what is happening there, you just follow this paper and read it. I just mentioned that this is not thermodynamical equilibrium. This is real time dynamics, full dynamics, and the results are presented here. The point is that I'm not able to discuss hydrodynamical simulations.
Okay.
Okay, the next question is from Petrov.
Victor, привет. I would like to ask the same question I made to the previous speaker concerning the dependence of all these effects, I mean rotational effects, and so on the collision energy. Because we know that the average impact parameter grows with energy. It means, if I'm right, that omega also grows with energy. And the answer to my question to the previous speakers concerning the effects was that with the growth of energy, all these effects relating with rotation in particular disappear. It seems to me a bit unnatural. What do you think about that?
Well, there are a lot of different ideas, I would say. I mean, ideas about collision, about dynamics in fireball. Well, and in my report, I presented results. I specified under what circumstances I found these results, and this is exactly what I presented. But what about hydrodynamical simulation or real dynamics? I don't know. We should try to apply different models and understand what is happening. Try to describe the data which were obtained in different experiments. But definitely, this is definitely when there is a collision, it is not possible to. It is not possible to say this is thermodynamical equilibrium. Nevertheless, we can study a system in thermodynamical equilibrium and obtain some results which might be important for real dynamics. And this is what I was trying to do.
Okay, we'll discuss maybe concerning general discussion. Thank you.
Yes, okay. So Arata, could you ask your question?
Could you explain again how Polyakov loop is measured? Polyakov loop depends on coordinate in this system.
Yes. We average overall volume, so we don't fix some particular place site on our lattice. So we average Polyakov loop over all volume. Yes, this is not homogeneous. Nevertheless, we don't just calculate. We have actually a calculation of Polyakov loop as a function of distance, but I haven't shown it here. We have such a calculations, But when we study critical temperature, we average overall volume.
Okay, you measure the average. My question is it possible to have a mixture of confinement and deconfinement matters?
It might be. We tried to find it. We haven't found it, but probably we spent not too much time to do this. In some case, it is so the idea is that probably it is possible to have confinement close to the rotation axis and deconfinement close to the boundary. But I don't know. Right now, I'm not able to say definitely that this can be realized.
Okay, thank you.
Okay, so I do not see further questions, but there are some comments and questions in the chat, but those questions and comments, I think we can discuss in the discussion session. What should we do? Maybe we close this session and then take a break and then go to the discussion session.
Yeah,
Before
sure.
that, let's thank Victor for this talk. Thank you, Victor.
Thank you for the invitation.